So the last type of hypothesis testing we're going to do is one about standard deviation or variance. So same notations, not going to bother writing all of these down this time. N is our sample size, S is our sample standard deviation, sigma is the true population standard deviation, or the one that's being used in the claim. S squared is sample variance, and then sigma squared is that population variance, or again, the one coming from the claim. You have two requirements that have to happen. Your sample observations have to be a simple random sample again. And remember when we were dealing with standard deviation and variance, we had that strict requirement that the population has to be normally distributed, because as a result, it gives us something that's chi-squared. So we're going to need to use the chi-squared distribution for everything. So for our test statistic, we're using that chi-squared distribution. So the way we find that is n minus 1 times the sample variance divided by the population variance. And it's the same statistic for whether you're testing standard deviation or variance. It's just a matter of, is the whole S squared given to you, or is just S given to you? So that's the only slight change. And then to find your critical values, to be able to figure out your rejection regions, you're going to use your chi-squared table with the degrees of freedom being 1 less than the sample size. But the problem is with chi-squared, remember, it's not symmetric. So if you have a two-tailed test, you're going to need to find those cutoff values separately. Now, doing this by hand for p-values is quite complicated, and realistically, even using a calculator online, it's a bit confusing. So we're really only going to focus on the critical value method here, because that's the only thing we can do by hand. So I want to go to our chi-squared table. So remember, this is going to give you the area to the right of your critical value. So slight difference than our other tables. So depending on the significance level, depending on whether it's a one-tailed or two-tailed test, if it's two-tailed, you have to, again, cut that area in half, and then you're going to figure out which of these correct percentages you want up there. So before we even try some examples going through and doing hypothesis testing, we're just going to find critical values and rejection regions for these different cases. So this first one, we have a right-tailed chi-squared test, a sample size of n equals 12, and a significance level of alpha being 10%. So I always like to draw a picture of these. For chi-squared, it starts at 0 and it's not symmetric, so our tail goes this way. They tell us it is a right-tailed test, so our cutoff is going to be somewhere here. And then this is the area that will be our rejection region. So this value is some chi-squared value. You might see it indicated with a 0 for a single valued test. Really doesn't make a difference for me though. But since it is a single value, our significance level is 10%. So this area should be 10%. The sample size is 12, so our degrees of freedom is 1 less. That is 11. So using my chart, I want the area to the right of this value. So the area to the right of the critical value is 10%. So using the table, we get that this critical value, which I'm calling chi-squared, is the following. Okay. So gotta go all the way back down again. My area to the right, because it's right-tailed, is 10%. That means I'm looking in this column here. My degrees of freedom is 11. So going down to 11, which is right here, my critical value is 17.275. So this value is 17.275. Okay. So this is the critical value. That means if you get a test statistic that is bigger than this amount, you fall into that rejection region and you're going to reject the null hypothesis. So the conclusion we get to make is we reject the null hypothesis if the test statistic is bigger than or equal to 17.275. Okay. Because that would mean it falls into this small percent chance area, so we are rejecting the null hypothesis. If I have a two-tailed chi-squared test with a sample size of n equals 19 and a significance level of alpha being 0.05, I need to figure out my two cutoff values because it's two-tailed. So I want to, again, draw a picture of what's going on here. This should be at 0. Didn't draw that too great. Should have drawn the bottom first. This is what our test looks like. So our degrees of freedom in this case is 1 less, which is 18. And I have two cutoff values for those two tails. The area is still going to be split evenly. So since the total area is 5%, the area in each tail is 5% divided by 2, which gives you 2.5%. So the area here should be 2.5%. The area here should be 2.5%. So again, these are not going to be symmetric, so I'm going to have two different chi-squared values. This one is our left critical value, and this one is our right. So starting with using the table to find this one, I know the area to the left of this critical number, but my table gives me the area to the right. So to figure that out, the area to the right of this critical value is 1 minus the 2.5%. So that would mean 97.5% of data falls to the right of this value. So I've got 18 degrees of freedom, and my area to the right should be 0.975. So going to my table again, my area to the right is 0.975, and I've got 18 as my degrees of freedom. So this critical value is 8.231. So the left value is 8.231. Now I need to figure out my right value. So here the area to the right of the right cutoff is exactly 2.5%. So this one's a little bit nicer. I just need to go into that table again. My area to the right is 2.5%. My degrees of freedom is still going to be 18, which is right here. So this critical value is 31.526. So in this instance, we are going to reject that null hypothesis if our test statistic, whatever that may be, is bigger than or equal to the right value, or if it's less than or equal to the left value. So again, that means it falls into either one of these places, which is that critical region. Okay. So we're going to just do 2 examples of this. We're going to do a 2-tailed test, and then we're going to do a 1-tailed test, and we're going to go through hypothesis testing and see, do we support or do we reject the claim, or do we fail to reject it? So starting off, this one doesn't have an exact application. It just gives us all of the different values. We want to use a chi-squared test to test the claim of sigma squared being 0.52 at an alpha equals 10% significance level, using the sample statistics of S squared being 0.45 and N being 17. And they tell us to assume that the population is normally distributed. So again, I want to start out with what is my claim? And in this case, it's that our population variance is exactly 0.52. Ooh, don't know why I did that. So since that has equal to, that's exactly our null hypothesis, which means our alternate is that our variance does not equal this amount. So this gives us a 2-tailed test. Should always start by doing this one. So I am going to have to go through and I'm going to have to find these critical values separately for these cutoffs. Okay. So filling in all of our values, our case here, our sample size is 17, which means our degrees of freedom is 16. Our population variance comes from the claim, which is 0.52. And then our sample variance, they tell us, is 0.45. So we can find our test statistic first, and then we'll find those critical values. So here for chi-squared, it's n minus 1 times the sample variance over the population variance. So that's 17 minus 1. S squared, we know the full thing, that's 0.45. And then sigma squared, we also know that full amount, it's 0.52. So trusting that you can plug this into your calculator, this should give you about 13.85. So now I want to figure out what are these 2 cutoff regions here. Okay, so I'm going to go ahead and I'm going to copy this because I want to be able to draw on it. So this one is going to be my left cutoff. This one is my right cutoff. And they tell us we want to use alpha being 10%. So the area in each tail is half of that. So we take the 10% and divide it in half, giving us the area in each tail being 5%. So 5% is here, 5% is here. Okay. So starting with finding the leftmost value, we know the area to the left is 5%. So the area to the right of the left endpoint is going to be 1 minus 5%, which is 95%. So this left cutoff value, we then can go to our table for. Remember, our degrees of freedom is 16, and the area to the right of this cutoff is 95%. So with our table, the area to the right is 95%, degrees of freedom is 16. So following those down, this critical value is 7.962. So that cutoff is exactly that. Then to figure out this one, I know the area to the right. This is 5%. So this value is the following. We need to scroll back down on our chart. We've got 5% area. Our degrees of freedom is going to be 16. So I need to go down to right here, and that gives us that critical value of 26.296. So this is 26.296. So getting kind of a cleaner picture as to what's going on, so I can label everything. Here are these two critical value cutoffs. This first one is 7.96. This second one over here is 26.296. So if our test statistic falls into either of these outer tails, we are going to reject that null hypothesis. But our test statistic we calculated is 13.85, and that falls somewhere in between. So since the test statistic does not fall in the rejection region, that means we fail to reject the null hypothesis. Okay. So what that means, I'm failing to reject the null hypothesis, which is my actual claim. So since I'm failing to reject it, there's not enough evidence to support it. It does not mean that the alternate is true. It's just I don't have enough evidence. Okay, so there is not enough evidence to support the claim. Let's try one more of these, and this will be a one-tailed test. This has quite a hefty just introduction, but the actual work is a lot shorter. So quarters are currently minted with weights that are normally distributed and having a standard deviation of 0.069. New equipment is being tested in an attempt to improve quality by reducing the variation. So currently this is our standard deviation, which we know is related to our variance. I want to see if we can reduce that. So they use a new equipment. So a simple random sample of 28 quarters is obtained from those manufactured with the new equipment, and this sample has a standard deviation of 0.043. We want to use a 1% significance level to test the claim that quarters manufactured with this new equipment have weights with standard deviations less than 0.069. So this new equipment with this particular sample, can I show that I have a better standard deviation? So to kind of just lay everything out into simpler pieces, our claim is that our standard deviation is now smaller than it was before. So that gives us more efficient machinery. So because this does not include inequality, this is going to be our alternate claim, which means our null hypothesis is equal, but also it really means it's the opposite case. So our standard deviation is greater than or equal to 0.069. So since our alternate has that less than symbol, we're going to be looking for a rejection region over here. And we want to see, is what we found significant? So this is a left-tailed test. Okay. So I'm going to go through and label all of our things. They told us the sample size that we took is from 28 quarters, which means our degrees of freedom is 27. Okay. The standard deviation is 0.069, and our sample standard deviation from these selected quarters is smaller at 0.43. So we want to test, is this significant, basically? And the level we're working with is 1%. So again, I definitely need to find what is that test statistic first, and then we'll find that critical region. So for chi-squared, it's n minus 1 times s squared over sigma squared. Now here, I'm just given s, so I do need to square it. So our test statistic is going to be 28 minus 1. We need to take 0.043 and square it. And then we're only given sigma, which is the standard deviation, but you need the variance in the bottom, so you need to square this 0.069. So plugging that into a calculator is going to give us a test statistic of 10.486. Okay. Now, with this particular left-tailed test, I have a single critical value, which again, you might just call it chi-squared. You can call it chi-0. We want 1%. So the area here needs to be 1%. But using my chi-squared table, I need the area to the right. So the area to the right of the critical value is 1 minus 1%, which is 99%. So this cutoff, using our table, degrees of freedom is 27, and we want 99% of area to the right. So I'm working in this, which means I gotta go all the way down though to degrees of freedom being 27. So that gives me a cutoff value of 12.879. So this is 12.879. Okay. So this value here is exactly that. Our test statistic is 10.48, which definitely falls in here. Okay. So since the test statistic falls in the rejection region, that means we are going to reject the null hypothesis. Okay. So if I'm rejecting the null hypothesis, that means there's evidence to support the claim that I'm giving, because the alternate is likely true. So likely this new equipment is giving a smaller standard deviation, and it is more efficient. So here there is evidence to support the claim. So likely the machinery is much more efficient and is giving us a standard deviation that is smaller than the prior one. So fantastic, that's what we want, okay? So again, you can use online calculators for p-values. Critical values is something we can utilize tables for in all of these different scenarios. The main thing is which particular thing are you doing a test on, That tells you the type of distribution, which tells you your test statistic, and then that tells you which tables you're going to use to find those critical regions. So very similar ideas for everything, it's just different distributions are involved for the different sample statistics.